Hello, welcome to the Suspensions Lab. Today in the lab we're going to be making two types of suspension, one mainly with calamine and one with bismuth, and we're going to be doing multiple formulations of both of those. What that will tell us is the effect of different conditions and different excipients on the stability of those formulations and the importance of that in practice. First of all though, what is a suspension? So, as you may have already seen, drugs aren't always very soluble in the liquids we want them to go into, typically water. So one way that we can make a liquid formulation with an insoluble drug is to just suspend a very fine powder of that drug through the liquid. So the solid drug is suspended through water, and so it becomes a suspension. Much like a suspension bridge is a bridge suspended by wires, the drug particles are suspended in a solvent, which again is typically water. But as you'll also know, solids tend to fall out of solution. They tend to drop down to the bottom of water, or they maybe rise up to the top. But in any case, they're not stable in water. And we typically see that because the things that we look at are quite large. If you took two stones and dropped them through some water, the denser, heavier stone of the two would fall faster. And so the same's true for powders of drugs when we put them into water. So we need to think about ways that we can actually keep the drug particles in suspension for longer. And one of the chief ways of doing that is to make sure that the particles are very small so that the rate in which they fall through the water is quite slow. One of the other ways that we do this is by putting wetting agents, which typically may be a surfactant, but might also be something such as a clay mineral. And what that does is it surrounds the particle and helps to keep it into suspension by having soluble parts that would like to go into solution, and helps to keep it into suspension as well. If you refer to your lab script, you'll see that I go into some of this in a little bit more detail. I then go on to talk about Stokes' law, which sort of outlines all of those factors that we can change to influence how fast something falls out of solution. And we can see we have the formula in your lab scripts, which is the velocity, the rate of sedimentation, is equal to 2 times the gravitational force, which we can't change, times the radius of the dispersed solid particles squared, and that's times by the difference in the densities of the dispersed and continuous phases. And that's all over 9 times the viscosity of the solution. So let's just have a look at all of that in some more detail and see how it actually makes sense. So let's forget about the gravitational field because we're not going to change that, we're not going to a different planet. But the radius of the dispersed solid particles, the smaller that radius, the slower it's going to fall through that water. And the change in densities. If our particle is much, much more dense than water, it's going to fall through faster. If, however, it had the same density as water, actually it would pretty much just stay where it is, and it maybe wouldn't even fall out of solution at all. If it had a lower density than water, then it would rise up to the top. And that's all over the viscosity of the liquid that we're using, the solvent that we're using. So if we think the more viscous a solvent is, the slower something will fall out of it. And the example I've got on here is if you were to take 2 pebbles and put those into and drop them into water and treacle or honey, then it would, of course, that pebble would fall through and sediment out. So sediment, meaning to go to the bottom, much quicker in water than it would in very viscous honey or treacle. So all of those factors will influence how fast a particle, be that a pebble, a grain of sand, or our drug particle, they will influence how fast that particle will sediment out of solution, will fall out of solution. And so they're some of the things that we can influence, and we will influence, to actually improve the stability of a formulation. Now moving on from there, in the script we talk about caking. So I've mentioned already that making the particle size smaller will improve the stability of a formulation that is a suspension. And that's true. However, eventually everything will fall out of solution and either cream rise to the top or sediment and go to the bottom. And if we've got a really, really, really fine particle size and they sediment very, very slowly, when they deposit on each other, there's not going to be an awful lot of water between the drug particles. And they'll pack very densely at the bottom and they'll form a cake of our drug particles. Hence it's called caking. Now that's an issue because they pack so tightly that you can't effectively resuspend or redisperse them just with simply shaking the mixture. And if you imagine a patient getting that at home and then the formulation has caked, they won't get any drug at all until they get to the very, very bottom where they'll just have a solid drug. So what's better, generally, is if we can say, well, okay, the formulation may slightly split and we may have some sedimentation, but if a patient is able to just shake that formulation and it becomes homogeneous again, it becomes the same all the way through again, then that's okay. That's better than caking. Ideally, we don't want it to fall out of solution at all, but if it's going to, we'd rather that it was a very loose falling out of solution that can be redispersed very easily with simple shaking. And so what we may do is we may accept that that's going to happen and then say, all right, we're going to put something in there that means when it does separate out, those particles aren't going to get too close to each other. They're going to stay far enough apart with enough water between them that when I shake that formulation, it will redisperse very quickly and easily. And those things that we put in are called flocculating agents. And again, it goes through this in the script as well for you, but there's two main types of flocculating agent that we may use. We may use electrolytes. Now this uses electrostatic forces to keep those particles further away from each other. If you imagine that your drug particles have charge on their surface, if all of those drug particles are positively charged, like magnets, positive and positive or negative and negative won't want to get too close to each other. And so with electrolytes in the solution, we can manipulate how far or how close or far those particles with charge can come to each other. But we have to be careful with that because you can then actually make the situation worse by shielding that charge such that those particles can actually come closer together than they would have previously. And that's what we're going to look at when we do the bismuth suspensions. We're going to look at different strengths of electrolyte solution. So we're going to be introducing different charge into that suspension, and we're going to see how well that stops particles from getting close to each other and how well that we can redisperse those suspensions after they do eventually split. One of the other ways that we can influence the flocculation is by using typically polymers, maybe natural or synthetic polymers, that will just physically hold those particles and stop them getting too close to each other. So it's almost like a big tree branch. If you threw lots of balls into it, those balls would all get trapped in different parts of the tree. And then if you wanted to redisperse them, you'd shake the tree and those balls would fall out. So that's what the polymer might be doing. It's got lots of branches and it will trap different drug particles, different parts of it, different branches like a tree. And then when you shake, they will be far enough apart from each other to come out of solution, to come out from there and go back into suspension. So we're also going to be making some calamine suspensions, and there you'll see the influence of some other excipients, and also you'll see the influence of viscosity on how fast suspensions will separate. So we'll get on with the lab now, and then after we've done the practical part, we'll be able to look through and sort of analyse some of that data and see what it means. Let's get going with part A of today's lab. I've got everything that I need in front of me, and it's actually a really quite straightforward part of the lab. We need simply to have bismuth subnitrate, which is a powder that we have here, and it's already at a set sort of particle size. It's a certain fine powder, and I'm going to need 5 stoppered measuring cylinders. So you can see we have a stopper in the top of these measuring cylinders. And 5 different strengths of an electrolyte solution. So this is monopotassium phosphate electrolyte. So 1 potassium and phosphate, monopotassium phosphate, all the way from 0, which is really just deionized water, all the way up to 320 millimolar solution of potassium phosphate. And essentially all I'm going to do is weigh out bismuth, weigh out 5 lots of bismuth at 2.5 grams, and make them up to 50 millilitres in the measuring cylinders. But we'll make an admixture first, where we put a small amount in, make a nice smooth mixture, fill it up to 50 millilitres, mix it, stopper them, and then what we're going to do is put all 5 of those suspensions next to each other, and then set a timer off. And then at set intervals, we're going to record the sedimentation ratio that is occurring in that suspension. And the sedimentation ratio, you can see, is defined at the bottom here in your script. So this is the ratio of volume of sediment divided by the total volume in the cylinder. So if you had no sedimentation, your total volume of sediment would be the full amount, essentially, because you'd have it all the way up the cylinder. Whereas if, say, for example, it's gone halfway down, you see a gap where you've got sedimentation halfway down the cylinder and the other half is clear liquid. That would be 25 millilitres divided by 50 millilitres, which would give you a sedimentation ratio of 0.5. And further down it goes, let's say you got down to 10 millilitres of actually having drug in it, and 40 millilitres having no drug in it, 10 and 40, that would be 10 millilitres divided by 50 millilitres, which would be a much smaller amount. So that would be 0.2 instead of 0.5 as a sedimentation ratio. So I'm going to get on with doing that. I'll just do one on camera so you can see it, and then I'll do all of the others, and then you'll be able to see them all in front of each other. So first of all, I need to weigh my bismuth. So I'm going to use a weighing boat for this. I'm going to zero my balance for that. And it says to weigh 2.5 grams of bismuth. Okay, that's fine. So I'll take that off, open up bismuth. Now this is a very large weighing boat, and it's actually taking up pretty much the whole of the scales. So I'm actually happy in this case to put the powder directly onto it, but if I do spill any, I need to make sure I clean it up after. And if you're ever unsure, you need to make sure you take the boat off and put the powder in somewhere else, and then put it back on. Okay, so I'm going to put this straight on. Being careful to try not to go over, because if I do, I won't be putting the powder back into this stop bottle. I'll have to put it into a spare weighing boat, and it will go in the solid waste later. And once I think it's on the money, I'll just put the cover on, just to be sure that I've got an accurate amount. 2.51 grams, good enough, I think. So we can take that off. And now this needs to go directly into the measuring cylinder. Now what you can do to help with this, particularly useful to use weighing boats, is that you can bend a weighing boat into a small sort of funnel, which will help us to get this in without spilling any. So I'll keep it flat until I'm happy it will go in, and then I can safely pour that in. There you are, without having spilt any. There we go. Wonderful. So that's in there now. I'm going to do this one with just the water. And so it says put around 15 millilitres in. Now we don't need to be accurate with this first part because we're just making an admixture. So that means a more concentrated mixture at the beginning. I put in 20 millilitres there, maybe a little too much, but we don't need to be accurate at this point. And then we're going to put the stopper in the top. And when you invert with the stopper in, we always keep a finger or a thumb over the stopper because you can't really trust them to stay in place. Okay, I'm going to give that quite a shake, making sure the stopper's still fixed. You can see the best cocktail impression. And once I'm happy that that's nice and homogeneous and is mixed through without any lumps, don't know if you can see at the top there, there's still a few little lumps. So I'm just going to give it a bit further of a shake. Once I'm happy that that's homogeneous with no lumps, we will then accurately top it up to the 50 millilitre mark. Now that's got stuff on it and it's going to go back in there. So good lab practice is either to keep it in my hand, which I will probably do, but if you're unable to do that, is to make sure it stays upright, or you put it on something that is clean already. So I'm probably just going to keep that between my thumb and forefinger whilst I hold this, and then accurately top it up to 50 millilitres. Now, I would lift that up normally, but for the sake of the camera, I will bend down and get that up to 50 millilitres. Okay, so I'm now just going to give that another mix with the stopper firmly in place. And that is the first of the suspensions made. I now need to repeat that process for the electrolyte strengths. Once they're all made, then they'll magically appear in just a second. We'll put them all next to each other and I'll put something behind them so you can see the difference, and then I will take pictures at the set intervals, which are at 10 minutes, 30 minutes and after an hour, I believe. Yeah, 10 minutes, 30 minutes and an hour. So I'll show you the starting point and I'll take pictures and put them into the video so you can see how that sedimentation went on over time between them. And then after we've finished that and recorded the results and done the next part of the lab, we'll then go on to analyse what that means. Now, just to finish off this first part of the lab, after having had the solutions sit for a prolonged period of time, we need to then have a look at how many inversions are required to redisperse properly each of them. And really, this is the most important part, because as we said, it doesn't really matter if it splits. What matters if it cakes. And so we'll go through all of them. So the first one here with water. Now, water looks quite good, but I'm not sure. I'm genuinely not sure. If we look at the top there, we can see there is splitting, and we've got this very flocculent-like part here, which has split. So it looks quite good. However, right at the bottom, and I'm not quite sure if the camera will focus on this, but right at the bottom, and I'll take a picture of it, there's a really, really dense layer at the bottom. Now, I don't know whether that's caked or not, so we'll see. Now, we'll see how many inversions it takes for this to be satisfactorily redispersed. So that's one inversion. Now, hopefully, actually, you can see now at the top, there's still that bit of maybe caking that I spoke about. So that's one inversion. That's two inversions. 3, 4. Let me do it in front of the camera. There we go. 5, and you can see we've still got the powder on the bottom there. 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, I've done 30 inversions, and we can still see that there's an awful lot of the powder at the bottom there. We do have some up here, but we've no idea of the concentration. So that's no good. So water on its own, no good. So number of inversions that are required were over 30. I'm not going to carry on any longer with that. So let's move on to this one, the lowest strength electrolyte, 1 millimolar. With the vast majority of them, we can see that this has gone down, and this ended up after over an hour, this ended up at about 2.5 over 50 for the sedimentation. Just going to write these down. Here we go. So yeah, 2.5 over 50. Yeah. And how many inversions is this going to require? Hopefully not as many. 1, 2, 3, and 4, I would say. 4 inversions. You can see there's nothing left on the bottom there. So I'm going to say for that, the 1 millimolar was 4 inversions. And now we've got the, oh, these aren't in the right order, the 10 millimolar. So that ended up at a final sedimentation volume of around about 3 mil over 50. And how many inversions are we going to require? 1, 2, 3. We've still got a little bit of a mess at the top with a few lumps. 4, 5. 5 looks pretty good to me. Okay, and then we'll do the same for all of these. 120, we had a final volume of around 4 over 50, as with the other one as well. But what's important, as we know, is how well it's going to redisperse. Okay, still got a bit of mess there. That's at 9 inversions, and the 10th to me looks pretty good. So that one took 10 inversions. It's getting worse. And we've got to 30 inversions again, and it's still not budging. So we can see that just the water and the very high strength electrolyte, it caked. So we've got caking, and then we've had, with all 3 of these other strengths, flocculation, because we've been able to adequately and with relatively few inversions redisperse, and then we've got to the higher strength where we've deflocculated. We've gone through flocculation to the point where we've got an electrolyte so strong that it is now deflocculated again, and it's still caking. And indeed, let's see if we can, even with shaking, just get this one in. You can see there we've still got the cake at the bottom, so I'm going to enjoy trying to wash that out later. Nope, not budging. And how about with just water? Let's give it a good shake. Nope, you can still see we've still got the powder right at the bottom. In fact, I would say that's worse because it's so compacted. So there we have it. That is the influence that the electrolyte strength can have on the medications. Too low, too high, no good, we can't give it. Goldilocks region, somewhere in the middle, where we get flocculation. We have formulations that, whilst they may fall apart, they can be mixed very easily. And we'll move on to the second part where we're making calamine lotions now. So now in the second part of this lab, we're going to be making up 5 different formulations of calamine lotion. And we're going to be putting different excipients into each one. We can see we've got calamine, of course, zinc oxide, bentonite, trisodium citrate, glycerin, and of course water as the vehicle, as the last part to make it up to the final volume. On that point, we can see here that it says water to 50 millilitres. Now, just to remind you again, that doesn't mean you add 50 millilitres of water. It means you add everything else first, and then you add enough water to top everything up till it reaches 50 millilitres as a final volume. So what we need to do here is we need to weigh all of our solid ingredients, and we're going to mix them together in a pestle and mortar. That's what we're going to do. So if I do this with the one that's got everything in for the video once, and then off video I'll make up all of the other formulations using exactly the same method, and then we'll be able to compare the different formulations to each other with the sedimentation ratio after an hour, and then seeing about the inversion tests. And we can have a little think about after the lab why it is different formulations here, whilst they haven't got anything in there to do with electrolytes, will change how fast these different formulations will sediment out. And one of the key ingredients that's the same in all of them that will slow this down is glycerin, which you will find is a very viscous liquid, and that will be changing the viscosity of the water to slow down that sedimentation process. So I'll get on and start putting all of the solid ingredients in, and of course we're going to weigh them out on the balance, and as if by magic I have a previously zeroed weighing boat here. So the first one that we need to do is to weigh out 7.5 grams of calamine. This is a very light powder. It's not very dense, so you'll see that I have to start putting in quite a lot. And again, I'm doing this on the balance, but if you're not going to clear up any powder that you spill, or you're worried about spilling too much powder, then you wouldn't do this on the balance. And I've put in a bit too much, so I'm taking it off into a spare weighing boat to go into the solid waste. Perfect. So that's going to go straight in. I'm going to use the same weighing boat just so I don't have to re-zero it, and they're all going to get mixed in here anyway. And we now need 2.5 grams of zinc oxide. I'm just going to give my spatula a wipe to make sure I'm not contaminating the zinc oxide. And again, I've gone over. I'm going to put the excess in this weighing boat. Now this wet excess, as I said, is going in the solid waste, so I'm not worried about mixing the different wastes. They're all going in the same one. Oh. Okay, now those two are in all of them because they're active ingredients. And then in this one, which is formulation C with everything in, 1.5 grams of bentonite. There we are. That's 1.5 grams of bentonite. And then 0.25 grams, so 250 milligrams of trisodium citrate. So much smaller amounts of this, so I'll be much more cautious in how much I put in. Much more accurate weighing from me there. Let's get that in there as well. Okay, so now, leave that there. Now we need to mix our dry ingredients. And if we see, it says here in the script, with a gentle motion, not applying a large amount of force, mix the ingredients in the pestle and mortar. For this gentle mixing, you can hold the pestle like a pen. There we are, like a pen, a very big pen, and then with just a gentle circular motion. I'm going to mix all these round. I'm not trying to crush it like you may in some other labs, or if you're trying to make an emulsion. We're just mixing. If I put too much shear force on here, we'll start to compact the powder together, which may make it hard to work with later, and we'll also reduce the powder size such that we may get more caking. So we've already got the powder size we want, and we don't want to reduce it anymore at this stage with the dry powder. Okay, so that's all mixed. And then using a measuring cylinder, measure the glycerin. Okay, so glycerin is really, really viscous. And let's see if I can do this in front of the camera. It's very gloopy, viscous liquid. And so to measure it accurately, we must be patient. And I'm just going to pour directly in. But it will take a while for it to reach the bottom of the measuring cylinder. So whilst I'm not pouring anymore, I need to allow the rest of this to come down because the volume is still slowly rising, which hopefully you can see. And equally, when we get this out, we're going to have to let it come out for quite a while as well to make sure we get it all from there. Now we can see I've over poured that, but I've already decanted out and I'm not going to use this again, so I'm just going to pour a little bit of that back in here. This isn't the stock bottle, so I'm not contaminating anyone else's work. You can see it's still a little high, so I'll pour a bit more out. Now, when I pour this out into the rest of the ingredients, I'm going to use a little bit of that water 250 millilitres to rinse out the measuring cylinder, just to make sure I get all of the glycerin out that I need. Excellent. So I'm at the stage where I can do that, and I know that we're going to have up to 50 millilitres. And so what I'm going to do is I'm going to put 30 millilitres of water into a measuring cylinder, roughly 30, and then use that to get everything that's in here and the glycerin to a pourable consistency. And then I know I won't have gone over my final volume. So let's pour the glycerin in as much as we can, as it is. It's dripping now and I'm starting to get a bit impatient with it. So what I'm going to do is, using a little funnel, pour some of this water I'm going to use in there. And I'm going to give it a little shake. So I'm going to reduce the viscosity of that glycerin so I can get that all nice and easily in. And I've emptied my measuring cylinder. Now let's put a little bit more water in. And I'm going to make an admixture again. Now again, we're not using a very large force here. All we want to do is get rid of the lumps of powder. So this admixture, this more concentrated mixture than the final one, lumps find it harder to escape away. Yeah, lumps of powder find it harder to escape away from you, and so you'll have a much easier time at making a smooth, lump-free formulation. And then once you've got it lump-free, you can loosen it off a little bit more, so it's a pouring consistency, and then pour it into the final measuring cylinder. I've still got some dry powder in there, so let's keep going. Now remember, just look at what I'm doing. It's not hard force holding the pestle and mortar like this, really pushing in. It really is strong enough to break lumps down, but not so strong that I'm going to be massively affecting the size of the powder. Okay, so then we've got rid of most of the lumps. I'm going to put a bit more water in to get this to a pouring consistency. And put it into the final measuring cylinder. Now once it's in the final measuring cylinder, you may wish to use a funnel as well to get it in, and you may wish to just scrape off any bits off the pestle, get them back in and make sure that they're incorporated. You may wish to use a funnel to now pour this into the measuring cylinder where it will stay. You can see a relatively smooth consistency coming out, but I do still have a few lumps in the bottom. That's okay. Now I've put this in the final cylinder, I know I've still got 18 millilitres of water to play with, which I can use to rinse out all the parts from here that haven't quite made it in. So I know I've got 18 millilitres to play with, so I'll make sure that I don't put any more than 18 millilitres in here. And I can use that to just rinse out as much of the residue from here as I can. And get rid of any little lumps I maybe didn't get rid of before. And that's the last bit, which I can do my final rinse with. And I'll be up to 50 millilitres. There we go. So now we're up to 50 millilitres, the final volume of the formulation, and I can give it a good shake, and we now can see we have a nice pale pink calamine formulation. So that was formulation C. I'm just going to mark it as such. I'll now carry on and make the other 4 formulations, and then I can put them at the end and we can have a look at their stability and see how well they fare against each other. So you can see at the beginning, we've got 5 formulations there all ready to sit and see if they're going to separate or not. And they will look pretty similar at the beginning, and we'll see how they look in an hour. So we're back after an hour, and the 5 formulations have been sitting here, and some of them have been slowly sedimenting and others haven't. I think what's clear is that all of these are better than most of the bismuth suspensions, but we do have a lot of other stuff in here, and they're different ingredients. So if we look at formulation A on the far left, this one was just calamine, zinc, glycerin and water, and we can see that we've got a very clear line of sedimentation there. So I would say that the volume for the sediment is 42 millilitres for that one. So we've got 42, and then you divide that by 50. Now for formulation B, I think that looks pretty homogeneous the whole way through. Pretty homogeneous the whole way through, so I would say that that hasn't sedimented at all, 50 over 50. And you can see, actually, if you've ever used calamine lotion before, that this one is looking a little bit like how that one does when it dries out at the top here. It goes all crusty, doesn't it? Now, formulation C, again, I can't see any sedimentation at formulation C. So 50 over 50 for that, if we were going to work out the sedimentation volume. It looks really nice, and we haven't even got this sort of cracking and drying at the top of this one. So formulation C is looking pretty good to me. Now moving on to formulation D. So formulation D, this one, what did that have in it? That has got calamine zinc oxide and trisodium citrate, and it hasn't got any bentonite in it. So B and C have got bentonite in them, these two here, and they're the ones that look pretty stable. Now D and E, they're the ones that are being stabilised with trisodium citrate, potentially. And I think we can see a clear line here where there's a split. Maybe it's not so clear on the camera, so I'm going to move the camera closer towards these two formulations. And hopefully you can see that at just above the 30 milliliter mark, and just below the 30 milliliter mark here, we've actually got splitting happening there. So for me, I would say that formulation D has got 31 millilitres, the volume of sediment, and formulation E has got, let's say, 28. And we would do the division 31 divided by 50 to work out the sedimentation ratio, and 28 divided by 50 to work out the sedimentation ratio. So we'll go into more depth on this, but I think what's pretty obvious is that the two formulations with bentonite have actually been far more stable over the hour, and the one without anything else in there, no clay, no trisodium citrate, bentonite being a clay, has a very, very clean split, and the ones with trisodium citrate, that maybe is stabilising it in another way, have a think about that, we've still got splitting, and it's splitting a lot further down than it is with just water and glycerin in there. So the last thing to check is to check how many inversions are going to be required for these to redisperse and be homogeneous. So I'm just going to put my gloves on again for this. Now I'm actually going to be touching them. Well, these are pretty safe, as you can imagine, given that it's something that we put on our skin. I'm going to take the first one. And I would say that was actually after just one inversion. One. These two, they're already fine. We'll double check that. There's no sedimentation. They require 0 inversions. Now, after a day or so, they probably would require some inversions because it's not going to be stable forever. And D, we can see we've got formulation split there. And again, just one inversion required. Final one. this one I'm just looking at more closely because I think if we look just at the bottom there, we can see there's some powder not resuspending there. So that's already had 3 inversions, 4, 5, 6, 7, 8. That's required 9 inversions. So we just had 1 and then 9. So what we can see here is that maybe this has flocculated and this has gone further and deflocculated. So we've got some caking going on at the bottom. Not so good. So we'll have a look at this in more depth in a bit. But whilst we're in the lab, my quick thing would be formulations with bentonite in them have been more stable, but maybe over a long time they would have cake potentially. I don't think so. And formulations with trisodium citrate only, not bentonite, have split more. And when we've gone too much trisodium citrate, sounds like an electrolyte, doesn't it? We've got deflocculation. I'm now out of the lab. I'm back home again in my preferred place to do the theory and analysis part of these labs with you. So in this lab so far, we've had a look at suspensions, and we know hopefully that a suspension is a good way of putting ingredients into a liquid formulation where they're a powder that's insoluble. So we're suspending an insoluble powder through an aqueous medium generally, and we can get a much higher dose than we can in solution typically, because if it's insoluble, it's a way of getting a uniform, homogeneous, fine powder through into a liquid formulation. And so that's what a suspension is. And you've learnt the influence, hopefully, of particle size on the stability of a suspension. That generally we want to make the particle size smaller, but if we get too small and we leave the suspension for too long, we might get caking, where those particles get so close together that we can't redisperse them. So we don't mind if our suspension splits into 2 parts where our solid drops. We don't mind that at all, just so long as when we give it a shake, we get a nice homogeneous suspension with all of those particles suspending equally throughout the whole liquid. To avoid caking, we may add flocculating agents. As I said, we don't mind if our formulation splits. Ideally it wouldn't, but generally it's going to as a suspension. And so we can add flocculating agents where we accept that it's going to split, and the flocculating agent may indeed actually increase the speed at which our suspension splits, but it stops those particles from getting too close together so that when we shake it, they can redisperse nice and easily through the suspension. And again, that doesn't stop them sedimenting, and in fact it may cause them to aggregate, but it means that we can easily redisperse and make a homogeneous suspension, which is really important for getting accurate dosing of our liquid medicine. So let's have a look at some of these questions in your lab script now. Question 1 has asked you to take a look at the results of section A and in table 3.1. And we can see the sedimentation ratio after 24 hours and the number of inversions needed to redisperse those different formulations. And we can see that that changes with different strengths of electrolytes. So you should be able to identify areas on, particularly in table 3.1, where we have no effect, essentially, where we have got the electrolyte causing flocculation, but a good flocculation, and where the suspension has deflocculated. So if you remember, a deflocculation is where we've gone past the point of the electrolyte doing anything useful. So our particles in suspension may have a charge on them. And by putting an electrolyte in, we're going to affect the ability of those particles to come close to each other. If we have 2 particles that are positively charged, they're naturally going to slightly repel each other. And we can map how close they can come to each other. And when we put electrolytes in, we may change how close they can come to each other. And that's what we're doing as a flocculating agent. And that may allow them to come closer together, but stop them getting very, very close to each other. And when we go past the point where we're just masking some charge and we allow them to get right into each other with the electrolyte, that's deflocculation. So nothing, flocculation, coming together, but it redisperses, and deflocculation, where they come together so close that we can't redisperse them. So we should be able to look at table 3.1 and make a decision as to where each of these areas is being seen. And so if I look at table 3.1, I can see that clearly the deionized water is doing nothing. But as soon as we put any electrolyte in, we can see that we're slightly changing what's going on. But when we get up to the strength of 1.5 millimolar of our potassium phosphate, we can see we get a change in the number of inversions we need to do to our cylinders for it to redisperse. So at 0.51 and 1.5 millimolars of our electrolyte, we're having to do 3 or 4 inversions for it to redisperse. And then when we get to 2.5, when we get to 2.5 millimolars, we go down to only needing 1 inversion for it to redisperse, which is much better and means that people only need to give it a very quick shake for it to redisperse. So I would say up to 1.5, the electrolyte isn't doing very much. Then at 2.5 to 80 millimolars, we're causing flocculation. That's the good bringing together, which is then easy to redisperse of these particles. Now, above 160 millimolars, you can see that we start to very, very quickly go up to the number of inversions required for it to be redispersed. And in fact, the data I found in the lab was that actually it wouldn't redisperse at 320. I did over 30 inversions, as you saw, and it didn't redisperse. So maybe I made that slightly differently to how this sample data was made originally. And at that point, then we will say that it's deflocculated. So we've got too much electrolyte in there and it's not doing the right amount of charge masking and allowing things to come together to a certain extent, and it's just bringing them all right into each other. So we've got the electrolyte doing nothing up to about 1.5 millimolar. Then we've got flocculation. And then from 160 millimolars, roughly, we're starting to get deflocculation, which we don't want. So if we were going to make this formulation, we would want to use something in the middle of that. So maybe we would use 5 or 10 millimolars of the electrolyte, and we'd have a formulation that, whilst wasn't stable, could very quickly be redispersed to a homogeneous suspension to make a good, accurate dosing liquid formulation. So question 3, we've used charge here to control the flocculation of a suspension. And we've shown that by changing the charge with the different strengths of electrolyte, we will affect stability. Now, particularly with children, some patients will want to dilute a suspension before they take it. Maybe amoxicillin suspension will typically be made up in the pharmacy, has to be kept in the fridge and has to be shaken before it's used, and maybe doesn't have a particularly pleasant taste. So you may get someone saying, well, can I dilute this with something that tastes nicer? So based on charge and stability, have a little think why some drinks can't be used to dilute a suspension and why that might be. Have a think, maybe pause, and then I'm just going to go through now why that is. So let's take the example of maybe orange juice or apple juice or something. You may have heard that they're acidic drinks, so not good for the enamel on your teeth because they're acidic. And that means that there's some charge knocking around in solution. And it's probably going to be hydrogen ions knocking around in solution. And we know already that charge is going to affect the stability of our suspension. And so that formulation would have been made specifically to have the right amount of electrolyte in. Let's say that electrolyte was putting hydrogen ions into solution. And we might add some more in with the orange juice, which might take it past the point of flocculation to the point of deflocculation. in which case we wouldn't have a stable formulation anymore, and we'd probably just get all of the medicine sitting at the bottom, and they wouldn't necessarily take that antibiotic in this case that they needed. So that's just one example with orange juice. Any other drink that has any electrolytes in it is the same, and that's pretty much all drinks. So if they wanted to dilute it, they could maybe use water, but even then maybe we wouldn't necessarily recommend that. And that's because the charge in solution for suspensions is really important. And that has some quite major implications as well for people who are being fed by feeding tubes, like that go straight into their stomach or go straight into their stomach through the skin as well. Those tubes are where medicines will be put down, and we need to make sure they don't block. And so if you put a suspension down there, and then you put some other sort of liquid, which is an electrolyte, which cause the suspension to fall out, you might then cake in the tube and cause a block. And if you cause a block in the tube that can't be cleared with a flush, the whole tube has to be taken out and replaced, which isn't something that we want to do on a regular basis. So this understanding of stability is really important in the delivery and the taking of medicines, particularly when it comes to suspensions and electrolytes. So let's move on to question 4, where we're looking at the calamine suspensions, where we're not focusing so much on electrolytes, we're looking at other ways that we can improve the stability of suspensions. And this is a suspension that is used topically, and it's not going to be swallowed. So maybe it's not so imperative, but still important, and it shows these theoretical points quite well. So we're going to think about section B, and particular the results in table 3.2. Here we've used different excipients to improve the stability of the suspension. Firstly, can you go through the table below and say the role of each of the ingredients and why that may improve the stability, if at all? I filled out a couple to show you the idea, and I suggest you pause the video here and have a look yourself at what you think they'll be doing in the formulation. Hopefully you've paused if you want to and had to think about that yourself. And I'll go through this table now with you. So we've got calamine in there, of course. That's the active pharmaceutical ingredient. It's in the name, calamine lotion. And this is used particularly on itchy lesions. So you may have used it for chicken pox, for example, as a child, to help reduce the itching in the area and make it sort of more bearable. Now, the impact on stability, the calamine is in fact a powder. And so the particle size of that powder will have an impact on how fast this sediments and whether it will cake or not. We've also got zinc oxide, which is actually a constituent part of calamine anyway, but in this case it's being used as a pigment to make it more white and creamy looking. And again, the particle size here will affect the sedimentation rate and whether the powder will cake or whether it won't cake. So we've also got bentonite. Now, I wonder what you found for bentonite. So this is a clay, and it's mainly made of montmorillonite, a certain type of clay. I've done work in the past with this clay that you can use it to load different drugs on, and it has charge in it, and it can release drugs at different points, and it's sometimes used in wound dressings. But in this case, we're using it as a stabilizer or a suspending agent. And so the amount of that we put in, and also the particle size again there, is going to affect how stable our formulation is. That's got charge on it again, remember. So that may be affecting the charge on the other particles. So the concentration that we put in of that may be important. We also have trisodium citrate, which is a preservative and a stabilizer again. So this is an electrolyte. So getting the right concentration of this electrolyte may help us to flocculate the solution, but too much, and we may deflocculate the solution, just like in the last part of this analysis. We've also put glycerin in there, which is a viscosity modifier. So you would have seen that it's very thick, viscous liquid, and by putting that into the formulation, we're increasing the viscosity of the formulation, which will slow the sedimentation rate. If you think again about dropping a little pebble into water or into honey, it will go through the water faster. It will sediment slower in the honey and faster in the water. And the same is true just at a smaller scale with using glycerin in our formulation. And finally, water, which is the vehicle or the diluent, the main body, and how we're moving this stuff about. And the viscosity of this will affect the sedimentation rate, but of course we're using the glycerin to regulate the viscosity of the water. So moving on from what all the different ingredients do, based on the sedimentation ratio, after 24 hours, and the number of inversions required to resuspend each of these 5 formulations, which of the calamine formulations do you think is best and why? So let's have a look at them again. So we've got A, B, C, D, and E. Now, in the video, when I was in the lab doing this, we saw that formulations B and C were the best after an hour. They redispersed straight away. They were fine. They didn't even need any redispersing in some cases. But after 24 hours, you can see that formulation B did need an inversion to redisperse, but formulation C didn't. Now, if we look back to the formulations, we can see that formulation C is the one that has absolutely everything in it. And we already said that bentonite and trisodium citrate are both stabilizers. And indeed, formulation C is the one where we've got both of those stabilizers in. Now, I would say if we look that B was slightly better than D. Now, B had bentonite in it and D had trisodium citrate in it. So maybe the bentonite is a slightly better stabilizer, or maybe not. Maybe that's just chance of what's happened in the lab. But we can see that the best formulation is the one that has got both of those stabilizers in it and has the full formulation, which in fact is sort of taken from the British Pharmacopoeia standards. And so why do you think this is best? Well, we've got 2 stabilizers in there to make sure that we don't get any caking and that we keep a nice homogeneous suspension. So question 6, according to Stokes' law, what are the formulation factors that may affect the sedimentation and the sedimentation rate of a suspension? Well, let's go back to the beginning of this lab where we've got Stokes' law written out. We've got V equals 2GA squared brackets rho 1 minus rho 2 and brackets over 9 nu, the little funny n. And we've just got all of those things defined. So this is basically your answer here. So the rate of sedimentation is V, and that is dependent on the gravitational constant. Well, we can't change that unless we're going to go to a different planet. A, the radius of the dispersed solid particles. We do change that. So if we have a bigger radius, we're going to have a different sedimentation rate to if we have a very small radius of our particles. We've got the different densities of the dispersed and the continuous phases respectively. Again, this makes sense. If we have a big disparity between the densities, one is, say for example, the particle is far more dense than the water, that's going to fall through much faster than it would if it had the same density. If something had the same density, it would just sort of stay where it was put. And if it had a lower density, it would rise up to the top. So if we have the same density as the water, it's just going to stay roughly where it is. If we have a lower density than the water, it will cream, it will rise up to the top. And if it's got a greater density, its tendency will be to sediment and fall to the bottom. And that's all over the viscosity of the continuous phase. So we have the continuous phase and we have our particles suspended in it. Let's say that it's more dense and it's going to fall through. We know a more viscous liquid, it will fall slower, and a less viscous liquid, it will fall faster. So they're all of the parameters that we can change that will affect the sedimentation of our particles. So all of these factors are really important when we store suspensions, as if we can't achieve a homogeneous suspension at the point of being used, we won't get even dosing throughout the bottle. If we have caking, we'll have no medication at the top of the bottle and we'll have too much at the bottom that can't even be used. And if we have creaming, we'll have a lot at the top and none at the bottom. And so your first few doses would have loads of medicine, maybe you'd overdose, and your last few doses would have absolutely nothing. So I've asked you to think about the implications that would have on the doses, which I've kind of just gone through there with you, and its effectiveness and safety. I'm sure you can go through in your heads as to why that is going to be important and the potentially large implications that could have on safety and effectiveness. And so this is why we must design formulations in the right way and understand how they work and implement that in our own practice.